In this video, we will prove a formula for the derivative of e to the x. So I want to begin by giving the definition of what e is. All right, so this says there is one value of b, so b is going to be some number, and there's one value of b that makes the limit as h goes to 0 of b to the h minus 1 over h. That makes that limit be 1. So I want to do a Desmos demo of this, but first off, if I were to just plug in h equals 0 into this, I would get b to the 0, which is 1, minus 1 on the top, and plugging in 0 for the bottom, I'd get 0 on the bottom. So this is 0 over 0, which is an indeterminate form. And it turns out there's going to be just one value of b that makes this limit equal 1. All right, so here we are in Desmos, and I have this function entered in. I've just changed the h's to an x. And I'm interested in seeing, well, what happens to this graph as the x value gets really, really close to 0. Technically, this function should have a hole there because I can't plug 0 in. It makes my denominator 0. But that just doesn't appear in a graphing software like Desmos unless I were to specifically tell it to put a hole there. And right now, I have b being equal to 10. And notice that when x equals 0, it seems like the graph is going through a number somewhere between 2 and 3. But as I make this b smaller, it crosses that y-axis at a lower and lower spot. And I'm interested in knowing, well, how small do I have to make b before it seems to cross it at 1? So I'm going to zoom in. Oops, let's zoom in a bit around 1. Make it smaller, make it smaller, make it smaller, make it smaller. That's pretty close. Look, we're at 2.7 now. And if you're familiar with e, that number will start to look familiar. Okay, so if I zoom in a little bit more, I'm a little bit below it. So if I do 2.73, okay, that's too big. 2.72, well, that's pretty close. If I zoom in more, it's a little bit above 2.71. And if you are familiar with the digits of e, the next digit would be 8, and that's pretty close. It's still not going to be quite right. It's still going to be a little bit off. If I change this and make it e, because Desmos knows a lot of the decimal digits of e, it seems to go perfectly through 1. And it turns out, if I zoom it out, that is, this decimal digit thing goes on forever, but this value of b will make that limit be 1. All right, so returning to our notes, it turns out that b, the number that does the trick, is about 2.71828 if I write the first 5 decimal digits. So this number, this decimal, this infinite decimal digit number, this shows up in a lot of places in mathematics, and we call it e. All right, and that is one of the definitions of e. It turns out there are many equivalent definitions. This just happens to be one of them, and this is going to be useful in finding the derivative of e to the x. So let's let f of x be equal to e to the x. Okay, there's something about e that's also special in terms of derivatives, and we'll see what that is after we do this derivative. So f prime of x is going to be equal to, let's do the limit as h approaches 0 of, let's use my definition, f of x plus h. We're using the limit definition of the derivative, minus f of x all over h. And now let's plug in. This is the limit as h goes to 0. If I plug in x plus h into the x, we get e to the x plus h. F of x is just e to the x, and then I have this over h. Okay, so we got the limit as h goes to 0. And with e to the x plus h, I can use exponent properties to write that as e to the x times e to the h. Because when I multiply two terms like this, I would add the powers. Okay, so this is, and then I get minus e to the x over the h. Okay, so we have the limit as h goes to 0. Now I see this e to the x on top in both of these terms. Let's factor that out. That leaves me with e to the h minus 1 over h on the denominator. Okay. So we're taking the limit as h goes to 0. E to the x has no h's in it, which means it's kind of like a constant for our purposes. I can bring it in front of this limit. And I get e to the h times the limit as h goes to 0 of e to the h minus 1 over h. And this is the limit that we know from the definition of e. This limit is going to be equal to 1. Whoops, I wrote e to the h here. This should be e to the x, though. This is e to the x. Okay, so what we end up with is e to the x times 1, which is just e to the x. So thus, what we've just shown is that the derivative of e to the x equals e to the x. So I'm going to box that. That is an important result. If I were to do this for any other exponential function, like if I were to change that e to some other base b, then this limit, it would be something, it just wouldn't be 1. And if it was something different, the derivative of that exponential function wouldn't just be itself. So one of the things that makes e to the x special is that its derivative is itself. And that happens because this other limit ended up just equaling 1. All right, so let's end this video by doing an example. So let's find the derivative of g of x. G of x is this function here. Okay, so the first thing that I'm going to do is, I notice that I know how to take the derivative of e to the x. That's just the formula that we got. And some of these other terms, but the e to the x plus 3 isn't something I know how to take the derivative of. I know how to take the derivative of e to the x, but e to the x plus 3 is different. So I'm going to simplify this using exponent properties first. This is e to the x plus, and we can rewrite that e to the x plus 3 and use this exponent property that we used before. This is e to the x times e to the 3. And let's keep the rest the same. X to the 3e plus ex. This is e times x. And now we are ready for the derivative. So for the derivative, g prime of x, derivative of e to the x is just e to the x. And then plus. For the next term, now I have an e to the x, and I like that. And the e to the third is a constant. And we know how to handle constants. When a constant is multiplying my function, the rest of the function, that constant stays there. So I will get e to the third still there, multiplying the derivative of e to the x, which is e to the x. On x to the 3e, this is x to a constant power. This is power rule. I bring the power down, 3e, and then times x to the 3e minus 1. I subtract 1 from the power. And then e times x, this is a constant times x. So this e is also a constant. And when I take the derivative of that, the e will stay there. It'll multiply by the derivative of the x. But the derivative of the x is just 1. We've seen that derivative before. And this is our answer. If the question asked me to simplify it, I could combine the e to the 3 times e to the x. But it didn't. So once we have finished taking the derivative, it would be okay to leave it like this. So in terms of our goals, we finished goal 4. We've proved a rule for the derivative of f of x equals e to the x.